Okay, imagine you're driving down the road and not paying attention too well, and suddenly notice that there's a stop sign up ahead, and you hit the brakes, slowing at a constant rate, a constant acceleration until you just get to a stop. And our question is, how much do you have to decelerate? What value of your acceleration do you need to have in order to get to that stop sign? Okay, so we're going to try and solve that problem focusing on the process. So to start, let's go ahead and draw the car at important times. So here's the car. I'm going to just draw a box. Forgive my lack of artistic ability. This is where you notice the stop sign. Okay, it takes a small amount of time, called a reaction time, to actually hit the brakes. So for the small amount of time, you're still traveling at a constant velocity. So we'll indicate that here. I'm going to draw a V, and I'll give it a subscript in a minute. Okay, and then you hit the brakes and you slow down, getting to the stop sign over here. So here's my stop sign. Okay, you get to the stop sign. So important thing is to label all the kinematic parameters: positions, velocities, accelerations, time. So what we can do, I'm going to do it above it. I'm going to say we have an x0 and a t0 and a v0. Okay. At this later time, I've moved some distance to got now to x1. At a later time, t1, and with a speed v1. Now I know I'm traveling at constant speed between these, so I know v0 equals v1, and I can show that later, but I'm going to be very careful to label every important point in this motion with its own kinematic value so that I'm emphasizing the process, because I could have had maybe a different acceleration here than here, and v1 wouldn't have been equal to v2. And so it's important to make sure we follow that process. The problems get far more complex, and the process is what's transferable and allows us to solve a variety of processes. So over here we have x2, t2, and v2. And again, I know v2 is 0. It stopped at the stop sign, but I'm going to put it here to make sure I'm cataloging all the variables that are important to then use in my tools, my equations, that relate how these variables together. Okay, so here is a process of acceleration. I've got an acceleration that's all assumed constant between these 2 points, but it's slowing down, and so like I showed the velocity here is that way, the velocity is still going this way, but slowing, meaning the acceleration is in the other direction. We call that a deceleration, but it's really an acceleration opposite the velocity. Okay, do I have everything? I've got positions for the 3 points that are important. I've got times. I've got velocities, and I've got showing that this is constant velocity here and constant acceleration here. So now I can make a list of knowns. Okay, what of these do I know? Well, I could say that my initial position is 0. I need to show that by drawing a coordinate system with my crosshairs there. So this now allows me to say x0 equals 0. And then I could always start my time whenever I want and to make it convenient. So I'll say t0 is also 0. Now v0, let's say that this car is traveling at 20 meters per second. Now I'm going to be efficient here. I know, since it's constant velocity, that between v0 and v1 it's moving the same. So I'm going to go and write v1 and then 20 meters per second. Okay. Alright, so I've done everything for this position. Now let's go to this position. x1, I don't know x1 yet. t1, I do. Let's say I know my reaction time is half a second. 0.5, and I'm going to choose an extra 0 here to indicate my knowledge of the sig figs. So that means I know these values to 2 sig figs. Okay, and that's seconds. v1, I've already listed what it is. I know that. Okay, now I'm moving across. A, I don't know that value. I'm going to be looking for that. So get over to here. x2, let's say that I know that the sign, when I see it relative to this point, when I first notice the sign, x2 is 60 meters away. The sign is 60 meters away. So I want to stop at that point. T2, I don't know what that is, but I do know V2. V2 is 0. Okay, so I've now listed everything I know, and I can now say, what am I looking for? I want to find A. I want to find what that acceleration is. Okay, I'm going to be a little bit careful here now, as I notice there are two separate types of motion: constant velocity, constant acceleration. Okay, as I get into the equations, I want to be able to differentiate between these two regions. This one has no acceleration, and this one has a constant acceleration greater than 0, or, well, sorry, it's with a magnitude not equal to 0. And so I want to actually establish an acceleration over here, okay, and make it different from this acceleration. This will be the acceleration following position 0 up till 1. This is the acceleration from position 1 to position 2. Okay, so I actually want to find 1, and I want to come down here and add that I know A0 equals 0. That's going to be important, and that is can relieve us from very common problems that happen where we include an acceleration in one part of a problem where it doesn't exist, or where it's a different value. And so being very careful to differentiate pieces of your motion. Okay, now with that care, we have now completed the pictorial representation for this. We have listed all the important parts of the motion, anywhere that's on the boundaries of a type of motion: constant velocity and constant acceleration. Okay, and so this position is the midway point between those two. We've listed all the variables associated with it: positions, times, velocities, and accelerations. And we've established a coordinate system, listing all our knowns, and particularly things that are 0 that we know are 0, and then stating what are we looking for. So with that now, all that care there taken care of, we can now effectively and accurately use our tools, our equations, that describe the relationship between all these variables. Okay, so let's start that. I want to find A1. Okay, so looking up here at A1 and knowing what's here, I know this one. I know this one. I don't know T2. I know this one, and I know this one. I don't know X1. Okay, I know both velocities. That's useful. And so that would turn my attention to the kinematic equation that relates acceleration with a change in the velocities. Okay, I do know one position. I know one time, but it's kind of the beginning time usually is not as useful. So let's try this one that uses both velocities. Maximize the number of knowns. So that one would be V2 squared equals V1 squared plus twice my acceleration. And again, here's where I'm putting in V1 or A1 because it's this acceleration, times my displacement, or my final position, minus my initial position. Okay. All right. Now, what things do I know? Well, I know it stops. V2 is 0 down here. Okay. V1 I know. That's good. Okay, X2 I know, and X1 I don't know, but I haven't used any of the information here, so I imagine, in fact I know, I can find X1 from this information. But let's go ahead and solve this in terms of the other variables. So solving for A1, I'm going to get, okay, first of all, if I subtract this to the other side, I'm going to have a negative V1 squared over 2 times X2 minus X1. That minus sign is important. Okay, I know that this is decelerating, and having chosen a coordinate system that's positive to the right, I should have gotten a negative sign for this. This is a positive value. X2 is larger than X1, so that's positive. So all of this is positive. That minus sign came from the algebra, and it correctly indicates that this is a negative acceleration. It's deceleration because my velocities are also to the right. Okay. Now, I could have, if I wanted to, knowing that that's going to be a negative, I could have put a minus 2a, and then my answer here would have been indicating the magnitude, because I already used that knowledge that that was a negative. Either way works, and sometimes I find it better to do it conceptually, knowing what is negative, and sometimes I think it's better to let the algebra show the answer. Okay, well with this, we could proceed and solve for that, except we still need to know x1. So we know everything else, v1, 2, x2. We need to find x1. So that means we need a pause, and we need to use other parts of the problem. So let's go over here to this one and see what is there that can help us find this unknown value. Okay, so looking at this one, this is constant speed, and so this one's going to be fairly easy. I know my initial position by my choice of coordinate system. I know my initial time by my choice of time. And I know my initial velocity. I know my final velocity. I know my final time. And I know that my acceleration is 0. So I have everything I need to solve for that one with the basic equation that says x1 equals x0 plus v0. Okay, t1 minus t0 for my delta t. Okay, and then plus a 1/2 a. Now which a is it? Is it this one? It's this one. Okay, that's why this is important. A0 t1 minus t0 squared. Okay. Now it would have been very easy for me to accidentally, because I had just solved for this, to plug A1 here. And I would have been in a loop trying to figure out which one's which. Okay, but though I've written this whole thing out, okay, being very careful to use my entire tool, okay, my entire equation, now I can clearly indicate that I understand that is 0, which I've written over here. Okay. I know that one's 0, so that's helpful. I know that one's 0. That's helpful. I know this one's 0. That's helpful. Okay, and then that allows me to be able to solve for this. So this a0 cancels this entire term, and so I'm just left with x1 is equal to v0 t1. Now you might be asking or saying, I knew that at the beginning. It's constant speed. I've done this in high school. You know, I could have written that immediately. Okay. Later in the semester, later in your study of physics, that's going to be fine. That's what I do too. But here we're trying to emphasize the process, because we're going to get to problems where it's not obvious that, oh, I can make these cancellations or this is the final answer. This process works all the time. You can solve complex problems this way. Okay, so yes, this came to a previously known answer, but this will work all the time. And so it's far more important to practice with this process on easy problems so you can focus on the process, so that you're ready, that process is ingrained in your mind and in your behavior as you start to attack complex problems. Okay, so now that we have this, we can now plug that into there and we could get our answer. Okay, so just this is basically where I'd say the problem ends, but so we can assess the final answer. You can say A1 is now equal to a negative, it's decelerating, v1 squared over twice x2 minus v0 t1. Okay, now if I plug in all my numbers there, I'm going to end up with a negative 4 meters per second squared. Okay, and I get the correct units as well. I have a meters squared or seconds squared, and this is a meters per second times a second. It gives you a meters, and this is meters. So I lose 1 meters, I end up with meters per second squared. Okay, and that is correct. Acceleration is the rate of change of, sorry, my page has drifted off the screen there. the rate of change of the velocity versus time. So it's meters per second per second. So I get this answer. Now, this is great. It's a number. We like numbers. I've got some good units, correct units to it. And the minus sign is accurate. It carried through properly. It's telling me it's slowing down, or the acceleration's to the left, as I've chosen to the right being positive, which is the direction of velocity. Okay, now it's really important not to just say, oh, I got an answer, now move on. Is say, does that number seem reasonable? This is called assessing. We need to assess our problems. So 4 meters per second squared, if it's starting 20 meters per second, okay, that means every second it decreases the speed by 4 meters per second. So after 1 second, this is down to about 16. After another second, this is down to about 12. And so it takes about 5 seconds overall to get to a 0 speed at that time. And that seems about reasonable. It seems, you know, if you're traveling 20 meters per second, that's about 45 miles an hour. 60 meters away, you hit the brakes and you start to slow down, then 5 seconds seems to be about a reasonable time to slow comfortably down to a stop. So 4 meters per second squared does seem reasonable. So I could put a check indicating that I have verbally here and in my mind thought about the reasonableness of this answer. And you should always, if it's a homework problem, write out your reasoning of why that number seems reasonable. And doing this assess catches me all the time. I might make a mistake, forget to square something, or forget to carry a 2 across. Just simple algebraic mistakes that will always happen. But the thing that denotes a good problem solver is when they get their number, they think about it. They think, what does this mean? If I'm off by a factor of 2, I'm like, oh, that just doesn't, maybe 10 seconds seems long, you know, how would I get that? And so you can figure that out fairly easily.